Circular motion is any type of motion that follows a circular path. Slightly distinct from rotational motion. Rotational motion, if you think of planets, is like the Earth spinning on its axis. That's more rotational. It's sort of circular as well, but we tend to group that as rotational motion. And then the whole planet's rotating around the sun. That would be a circular motion more precisely. Lots of examples of circular motion: wheels on cars going around and around, cars turning corners. So you could imagine that this is a car with the spokes on the wheel, or a bike, and it's going around and around. You could have this as a circular track with a little car zooming around it. That's circular motion. A hammer throw, where you've got a person with a mass and they're sort of swinging it round and around and around, standing there, and it goes around in a circle. That's an Olympic thing. Olympics coming up this year. You might have the propeller on a plane, an airplane. There's the front of the plane. Maybe some wings sticking out the side as well. A canopy. You don't need all that, but the blades themselves that are rotating around and around, that's circular motion. The propeller on a boat, or the other classic one is a merry-go-round. This could be a merry-go-round now, and you've got kids that are standing on top and holding and pushing with their feet over here, and they're trying to go faster and faster and faster around it so that they can vomit. That'll be great. You never usually vomit as a kid, you just feel dizzy and have a fun time with that. But anyway, that's circular motion. Some important information on circular motion. We are usually interested in how fast the circular motion is occurring, and there's a couple of ways that we can measure that. We can measure the number of turns per second. Okay, that's also known as the frequency. So the frequency is measured in cycles per second, or hertz. Hz is the symbol, hertz, H like hertz for a car. Good advertising, no affiliate in any way. So that's linked. Another way is the period, so how long it takes for a single rotation to go once around. So period is a time thing measured in seconds. And what else can we have? We can actually have the instantaneous velocity, or just the speed that the surface rotates at. So we've got the speed of rotation at a particular radius. So that would be measured in meters per second. Okay, so there's a lot of different ways that we can look at this measurement of speed. Each of them will have their different units, but they're all relatively interchangeable. I'll give you an example of a very interchangeable part. The formula for frequency is 1 over the period. So that's really nice, that period and frequency are related. That also means that the other unit for frequency is seconds to the negative 1, or just inverse seconds, because 1 over seconds is 1 over period. What else have we got? Other important information. There's usually forces involved with circular motion. So let's just redraw something down here. Where's my pencil? There it is. So here's your circular motion. You've got a mass or an object. This could be the top view of a mass on a string, and it's rotating around that way. There's a couple of things going on here actually. We've got to write them all down as important. We've got the instantaneous velocity, and that's at a right angle to the radius, to the radial point. The radius itself is another important bit of information, the radius being the distance from the centre to the outside. We've got something causing this motion, and it might not be immediately obvious, but usually when there is motion occurring, for it to have started up and to be undergoing change in speed or something like that, there's usually a force, an unbalanced force. and let's see if we can identify where the unbalanced force is in this case, because the velocity is definitely changing. As soon as the mass comes around to another point here, the instantaneous velocity is now in a different direction. So that change in direction, that means that there must be a force applied. And for there to be a change in direction, that means that there is a change in velocity. Okay, so I'm following a couple of things here. We'll write change as a triangle, change in velocity. That tells us that there is an acceleration occurring. So there's actually quite a lot going on with something simple like circular motion. Now this is just an overview, so we'll get into each of these things in a bit more detail another time, but one other major thing that we can look at is this force that's causing the change. Might not be immediately obvious, but it's towards the centre. And let's get another colour because it's becoming a bit hard to see what's going on there. Here's my green, and it's towards the centre. That's where our force is. And why that is because your velocity has changed direction. It's changed direction towards the centre of rotation, perpendicular again to the direction that its instantaneous velocity is. And you imagine if you're swinging like a bucket around and you're trying to keep the water from falling out, that's how we draw that. We have like a circular thing like this. We've got a person standing in the middle, handle of the bucket, that's their arm with their hand holding on, and this is the bucket itself, and it's got water in the bottom. And they're swinging it around one way or the other, doesn't matter, and the water doesn't fall out. But if you've done this before, you'll know that your arm pulls like crazy. You'll feel quite a significant pulling in your arm, and that's the tension force. We could write that Ft so we don't confuse it with the period. So the tension force is what's causing this acceleration, and you're pulling it down towards the centre. Okay, and when it's at the bottom, you're pulling it upwards, so there's definitely a force being applied to change the direction. It's really important. This is what we call the centripetal force. Centripetal. Okay, centripetal means centre seeking. Like the petals on a flower have all these little kind of pointy bits pointing towards the middle, centre seeking. Okay, you can imagine that and remember that yourself, and then it's got a bit in the middle, that's nice. Anyway, so centripetal. You might have heard about something called centrifugal force, and just so that you know, it doesn't exist. Centrifugal force doesn't exist. It's an imaginary force. There's a centrifugal type of effect, which is like if you get a centrifuge and you put, we'll just make this flower a centrifuge now, and we've got little vials of blood and canisters on the end. There's another one hanging out here, and as it spins around, it separates out different densities, so that you get higher and lower densities at different levels. That's a consequence of having the same centripetal force with different densities of mass, and they'll separate themselves out. But it's a little bit like the heavier parts that have more inertia or a greater mass that are harder to rotate. They get left behind and they go further out as you rotate this thing around. But anyway, that's something to ponder another time. There's a few more equations to look at acceleration and such, but we'll have to. That's just the general overview, and that's circular motion.